Core Java is an object-oriented language that serves as the bedrock for massive enterprise applications and the automation frameworks used to test them. At this scale, executing a single script requires managing millions of data points every second. Mastering automation in Java requires looking past the code on the screen and understanding how the computer physically manages that data in its memory. Dynamically typed languages, like Python, estimate a variable's memory footprint at runtime. These shift and resize continuously to accommodate incoming data. Java requires explicit typing before the program even compiles. You must define the exact parameters of your data before it enters the system. This strictness is dictated by the physical architecture of computing hardware. This is random access memory, or RAM. It is the temporary physical workspace where all runtime data must live while an automation script is executing. Enterprise applications scale across thousands of servers exactly like these. In this environment, memory is a finite, highly controlled resource. Java's strict data typing is a mechanism for deterministic RAM allocation. By defining variable sizes upfront, the system avoids the overhead of runtime estimation, ensuring predictable performance in high-stakes environments. A variable is a reserved physical container located within the temporary memory grid. Declaring that variable creates a reference point, allowing the Java compiler to find and retrieve stored information, such as the number 10. The Java compiler cannot guess what shape or size this container needs to be once the program starts running. The programmer must explicitly declare the data type, so Java can assign exact byte parameters to that specific memory space. Think of memory allocation like seating guests in a restaurant. If a dynamic language hoards memory by assigning an 8-person table to a single diner, total capacity drops. Explicit typing reserves exactly what is needed, allowing the layout to accommodate more processes. Without strict sizing rules, automation frameworks would rapidly exhaust available memory, leading to fatal execution errors as the script runs out of room to operate. Java organizes these footprints into two main categories, starting with primitive data types. Primitives are atomic units. They are the simplest, indivisible containers that hold exactly one value. The numerical hierarchy begins with the byte, which occupies a single 8-bit grid square of memory. For whole numbers used in most loops and scripts, you declare an int, which occupies exactly 4 bytes of space. If a numerical range exceeds the integer limit, the long data type expands to cover 8 bytes of memory. Precise decimals, like those required for financial calculations, use the double type, which also reserves 8 bytes. To store single letters or symbols, a char reserves a specific 2-byte footprint. All conditional logic is driven by the Boolean type, a 1-byte switch that snaps between true and false states. By utilizing these specific primitive shapes, engineers sculpt automation scripts with surgical memory efficiency, preventing bloat before a single line of code is run. The second category includes structures designed to handle multiple values simultaneously. An array is a method of storing a grouped sequence of identical primitive types, such as a set of integer test scores. Arrays are restricted to a single data type. They cannot store text alongside an integer ID. Representing complex entities, like a user profile with mixed data types, requires the use of objects. A class is a theoretical blueprint mapping out the properties and behaviors of a composite entity. An object is the physical realization of that blueprint, loaded into memory when the program executes. In Java, a string is a non-primitive object. A string bundles multiple character types together alongside built-in modification behaviors, known as methods. Object-oriented structures allow QA engineers to model massive dynamic test targets, like entire login pages or user profiles, directly into the physical RAM. Applying these concepts requires manipulating these memory blocks to compute a result. For a simple interest calculation, we initialize variables with specific types, such as double for the principal and rate, creating the necessary memory spaces. The assignment operator binds the final value calculated on the right to the pre-allocated memory space on the left. Arithmetic operators orchestrate the logic, using the asterisk for multiplication and the / for division to reach the final result. The compiler utilizes the defined byte sizes of these double and int types to ensure the math remains accurate and does not overflow during execution. The addition operator behaves uniquely when encountering strings, resulting in concatenation rather than a mathematical sum. This process completes the journey from hardware limits to defined variable sizes and the execution of logic. Once these memory spaces are assigned and initialized, you can use loops and conditional statements to control the flow of execution. Respecting Java's memory architecture allows you to move beyond basic syntax toward building automation that functions reliably within the hardware's limits.